Hi, can you hear me online?
Yes, sir.
Okay. Okay, so let's get started. I think today 10th standard students have their MPI exam, so we don't have lots of students today. But anyway, we'll continue with some topic related to geometric transformation that we have been doing. But now today, what I want to focus more on is the algebra part of it. So I briefly talked about group maybe in one of the previous lectures, but I want to emphasize that how the group theory is really central to the topic of transformation. And if you read, so let me give the names of the most important books on transformation. Okay, so if anybody is interested to read more about this is a series of books called Geometric Transformations. It's a series of four books actually, one to four. Author is I. M. Yaglom. He's a Russian author. And roughly speaking, the way the book is divided is that each volume talks about one kind of transformation. So first book which we are largely covering is the congruence transformation, right? So congruence transformation are the translation, rotation, and reflection. Then the second book talks about similarity transformation. So that is homothety, which maybe you have already studied in some context, like homothety of 9-point circle and the circumcircle. Third book talks about, I think, projective transformation. So projective transformation is a very interesting, different way of transforming the plane. And the fourth one talks about inversion. So inversion, to some extent, we have already done, but we'll go into much more detail. Okay. So this is roughly the division of the topics. And Yaglom does something very interesting. At the start of each book, he has a small essay. And like over the course of 3-4 books, he tries to answer one very important question. And for me personally, this author and all these books have been very important in understanding geometry. It changed the view of geometry completely. And so if you want, you can just read those first few. I think you will find all these books online anyway because they're out of copyright for a long time. But the question he tries to answer is, what is geometry? It's a very important question that we have been doing geometry for a long time. But have you tried to write a definition of geometry? That what you call geometry? So that there he really talks about, we can describe the geometry is the study of some properties. But the whole question is, which properties are you interested in? Like, for example, if I draw a triangle here, okay, triangle ABC, and we say we want to study the properties of this triangle. So, do we consider that the color of this pen is white is a property, or the thickness of the pen is a property, or does it matter whether I draw the triangle here or here? If it is the same triangle, does it really matter where I draw it on the board? So what is the property that we are trying to study? And like just to give you the final conclusion, that what he's saying is that the properties that we study are those properties we don't change under the transformation. That if you apply geometric transformation, like if you rotate this triangle by 90 degrees and you make it like this, do the properties that we care about change? No. So those are the properties. That the properties that don't change under transformation are the properties that we care about. And that is what the study of geometry is. So that is the conclusion of his essay. But the way he develops it is very nice. And what he actually, if you are interested, he shows that what we call geometry is only a small part of a much larger theory. That we can talk about geometry in a much more broader context. And that is what he talks about. So very interesting series of books. And it is worth spending the time understanding this because it will really change the view of geometry for you. Okay. So I won't be able to go into the complete detail of what he does, but just to give a small introduction through what I want to say, group theory. So, okay, so let me just, I may have stated the axioms of the groups before, but let me just state it again, that what is a group? Okay, let us start with what is a group, because I don't know if everybody is on the same page with this. So let me define a group formally. So basically we have to consider set. So consider a set. Okay, so you need a set. So these are the set of the objects on which we are going to do some operation. Then we need to define an operation. And typically we consider binary operation, that is operation that takes two inputs and generates one output, right? So for example, typically we denote the operation by multiplication. Okay. So this is a operation that goes from G cross G to G. Okay. Don't get confused that this is also cross, this is also cross. This is the multiplication symbol, and this is the Cartesian product of the set with itself. So in other words, two inputs and one output. Okay, so this is the multiplication, and such that so some properties that the operation has to satisfy, and these are kind of common sense properties which we already know from our experience. Like for example, associativity. That if I have three numbers, does it matter in what order I multiply them? I can, for example, if I have A into B into C. So suppose somebody does A into B followed by C, and somebody can first multiply B and C together, and to that they'll multiply A. So they can change the order in which they multiply, but the answer is going to be the same. So this is the first property, which is called associate, and this is has to be true for all ABC in our set. Okay, so this is called associate. Okay. Then the second property is that we have to have a special element, which we call additive identity or multiplicative identity. So there exists an element typically denoted by 1, such that. So what this 1 has to do is that if you multiply any number by 1, you should get the same result back, right? So A into 1 is the same as 1 into A and 1 into A. So this is called existence of identity. Okay. And third property is that whenever you have this identity, you also have the concept of inverse, right? Like we have reciprocals in numbers. So any number, if you take any element of the set G, there has to exist another element, we typically denote by A raised to minus 1, such that if you multiply these two together, you'll always get 1. So this is called existence of inverse. So any set G along with such a function which satisfies this property, then we say that G is a group under that operation. Okay.
Set G is what? Integer,
It can be anything.
real, unreal.
It can be the set of elephants. It can be the set of countries. It can be the set of students sitting in this classroom. But whatever definition, you have to have this operation of multiplying two elements together. So that is what you have. So important that when you say G is a group, you have to say what is the operation you are defining, because on the same set you could have different operations and each of them will generate a different group. So we'll see examples of this, that how the same set can have different operations on that. Okay. One thing you may notice is kind of missing from this list is that what we call commutativity, that we know that A into B is equal to B into A, right? Like 5 plus 3 is the same as 3 plus 5. But that is not part of the group definition. So group does not have that requirement. Some special groups have that additional property. So we have a different name for that. So if along with these three properties, if property 4 is also satisfied. So what is property 4? Let me write. I should have written it before. That if any property 4 is what we call commutativity. That for any two elements of that group, if it is true that A into B is the same as B into A, which is called commutative law. So if 4 is also satisfied, . then we call G as a commutative group. Okay, but not every group is commutative, as we have seen last time also.
Where also you have A into B into C.
There the order bracketing, it's only bracket, but if you observe closely, there I did not change the order from left to right. A was first here, A is first here also.
Yeah, bracket is changed.
Only bracketing is changed. Here the order itself is reversed. And like we have example where it may be surprising to see that whether this is true, but this is not true. But we have examples of this. Okay. So just to share one example of a group, and we may have seen this before. But so if you take modulo any divisor, like let us take modulo 12. Okay. So consider the example. Consider the set Z12. Okay. So Z12 denotes all the remainders if you divide by 12. Okay. So in other words, this is the set of all the numbers from 0 to 1 to 11. Okay. These are all the possible remainders if I divide by 12. And the operation I'm going to consider is addition. So addition can be defined on this set, right? If I take any two elements of this set and I add them, and again the result which I get, again I will take modulo 12. So this is the operation of addition. So adding two numbers, you get one more number. So do you see that under this operation, this is going to be a group? Because if you go back to those results, firstly, is it commutative or is it associative? Like if you have any elements of this set, right, A, B, C belonging to Z12, does it matter in what order I add them? Because finally I'm going to take the remainder modulo 12, right? So it doesn't really matter that whether you add them this way or this way. So this is satisfied. Then is there an identity element in this set? What is the identity element? The 0, right? Because if you add anything to 0, you will get back the same number, right? So 0 is the identity. And what about inverse? Does every element have an inverse in this set? Like for example, what is the inverse of 1? Inverse of 1 will be 11, right? So like that you can match up the pairs. Inverse of 1 is 11, 2 is 10. And if you notice, interestingly, inverse of 6 is itself. So number can be its own inverse. And what are the inverse of 0? 0 is 0. So 0 and 6 are both interesting number. They are their own inverse. But every number has an inverse, right? And in addition, this set is also commutative because basically addition is commutative, right? If you add A plus B or B plus A, you are going to get the same result. So this Z. So what we can say because of all of this is that Z12 is a commutative group. Under addition.
I have a way.
Yes.
0 to 11 written are the remainders.
Hmm.
And divided by 12.
Yes.
So I have a concept.
Mm-hmm.
Instead of calling inverse of 1 is 11,
Mm-hmm.
you can say co-remainder of 1 is 11.
Co-remainder. So the problem is the word co-remainder is only corresponding to this example,
Yes.
but we are going to see groups in every context where it is not division. So the word inverse is much more general. We can use the word co-remainder for this example, but for the general group theory, we need something like inverse. Okay, and you will observe that there's nothing special about the divisor 12. You could take any divisor, right? So for every divisor, you are going to get one group, right? Just like we wrote Z12 here, we could take Z11, Z10, Z9. Every number will have its own group. Okay. Okay, but I took the example Z12 deliberately because there is something very interesting that happens in Z12, right? If I observe the structure of Z12, so if I write all the numbers like 0, 1, 2, 3, okay, what I can do is I'll can partition this into smaller set such that, for example, consider the set 0, 3, 6, 9. Okay. So you see this is a subset of Z12, right? Okay. And now answer the question, is this also group? The operation is the same. We are still doing everything modulo 12, but now we are only going to remain in this group. So the question is, is this a group? And technically speaking, somebody would like to write the operation that we're doing, the addition. That operation does not tell us that we are doing modulo 12. So maybe somebody would like to write a small subscript there, like plus 12, to indicate that it is addition modulo 12, but we are just not being that diligent about it. So if you think about it, you can try it. Like if you take any two numbers out of this set and add them, it is a group. You see, because again, associativity is true, identity element is there, inverse, all the inverses captured here? What is the inverse of 3? 9, right? So it is there in this set. So the important thing is that applying that operation, the answer always remains within this set. And not every subset has this property. Like for example, if somebody thinks that I think 0, 1, 2, 3 is also a group, this is not a group. Why? Because within this set, the answer can go outside the set, which is not allowed. Like 2 plus 3 is 5, which is not in the set. So this is not a group, but this is a group. Okay. But notice this is a group inside another group. So therefore, we have a different name for this. We call this a subgroup. Okay. Just as you have a concept of a subset, this is a subgroup. Okay. So this is a group. So the answer is yes. So this is a group. So this is called subgroup of our original group, Z12. So the most important property of subgroup is what we call closure. So actually some textbook will have this additional property at the top. If I just go back to the previous part for a minute. Here we wrote the rule 1, 2, 3, right? Some textbooks you will find there is a rule 0 also here, okay? And that rule 0 I prefer not to write because it is captured in this definition. So when we define a function this way, it is implicit that the output is in this set G. So when you multiply to or add to numbers of this first two set, you will get an output which is in this set. But some authors will write it explicitly. So I'll just write it as rule 0 at the top. Okay. So rule 0 is called closure. So what it says is that if you have to take any two elements in the set, the answer of the product is also in the set. We call it a closure property. Okay. So if you take any two elements of the G and you multiply them or add what is the operation is, the answer should also be in the same set G. So for a group, this closure is a trivial thing, but for a subgroup, this is very important that it will be a subgroup only if it is closed. Okay. So now the first question I would like to ask is, can you find any other subgroups of the Z12? Or is that 0369 the only subgroup?
Can you go the commutativity part? Sorry.
What about that? So you can see that Z12 is also commutative because any number, for example, 3 plus 6 and 6 plus 3, you are going to get the same answer, right? So
no,
this
the
is
commutativity, the previous slide part.
previous slide. Okay. So in general, every group will not be commutative, but if a group has this property that the order of multiplication does not matter, then we call it commutative. And I think last time I showed example, like the rotation group, if you remember, is not commutative. We had shown that example, right? If you rotate an object around x-axis and y-axis, but somebody first rotate around y-axis, then x-axis, the answer will be different. So rotation is not commutative. So again, I'll give you some time to think that is there any other subgroup of the Z12 or that 0369 is the only subgroup? Question. Let us try to find all the subgroups of Z12.
The first associativity,
Mm-hmm.
but it requires three elements to like
Yes,
define a group.
yes.
But if a group has two elements, then
No, but the thing is, ABC need not be distinct.
okay.
Yes. So we never said they have to be distinct. In none of the previous cases, we are saying the have to be distinct. Even commutativity, A and B can be the same, but it is a trivial statement, right? A into A is obviously A into A. So are you finding any other subgroup?
Set containing zero.
Yes, only zero, right? So that is the most trivial subgroup that you can think of. So consider the set of only the element zero. This is a subgroup.
They're even numbers. 0
Even numbers, yes. So the set containing only the element zero is a subgroup because it is closed. Most important property you have to check is closure under the operation. So 0 into 0, 0 plus 0 is 0, right? So it is closed. So this is a subgroup. Then Anushka is suggesting even numbers, correct? This is also a subgroup. Then we already have the example 0369. This is also a subgroup. Any other example? Yes.
Only
Yes. No, but the problem is, so the example which you have written here is 0, 1, 11. See, I can add an element to itself, right? So what if I add 1 plus 1? 2. So that won't work, right? Any other example?
06.
Yes, 06, correct. Then 048 also. So you see, every divisor of the 12 is generating one subgroup. If you notice, say the first element 2, 3, 4, 6. If you take the divisor of 12 and you take all multiples of that, that is creating a subgroup. So you see one element is missing in this list. One element is missing in this list. We have captured all the subgroup, we missed one element. Anybody think what is that element?
039.
No, if you take 039, 3 plus 3, 6 is not in that set. Basically, if you take a number, you have to take all its multiples, right? Because you keep on adding the number to itself. Okay, the example we missed is what about the Z12 itself? A set is its own subset, right? So just like the element 0 is like something we call trivial subset. In the same way, if you just take, suppose somebody decided I want to include 0 and I want to include 1. As soon as you include 1, you have to include 1 plus 1, correct? And 3 and so on. So the entire Z12. So Z12 is its own subgroup also. Just as you say, every number is its own divisor. Every group is its own subgroup. So Z12 has how many subgroups? 1, 2, 3, 4, 5, 6. Okay. So maybe based on this, you can, as a homework, try to answer this general question that given any natural number n, I can define Zn similarly. So Zn has how many subgroups? So two questions for you to answer, because here I have not fully addressed why there cannot be any other subgroup. So this is something that you should try to prove. So question 1, for any natural number, how many subgroup it has? And as part of that, prove that no other subgroup can exist. So for 12 also, we have not answered the question. Can there be any other subgroup apart from what you listed here, or these are all the possible subgroups? Okay. So now you may be having the question that are we going to do geometry or not? Huh. So geometry is not involved in this, but this is going to be very important for geometry, as we are going to see.
So now we have to find how to find the answer of subgroups.
For any natural number n.
Yeah.
And most importantly, see from based on this example, we can see that we can take the divisor of that n and use that to create the subgroup. But what you have to answer is why no other possibility is there? Why every time you have to start with a divisor? Because technically there are 12 elements. How many subsets are possible of a 12 element set? 2 raised to 12, right? Every number has a yes or no, yes or no. So out of 2 raised to 12 possible subset, what is so special about these 6 subset? That only these are the possible group, no other group can exist. That is what. Mhm.
As we practice the 12 times,
Yes,
those will be subgroups are possible.
that is what we looks like from this example. But we need a proof that no other possibility is there. Mhm. Okay, so anyway, this is for you to think at home. We are not going to study that here. Okay, but I hope from this example the concept of subgroup is understood. Okay, and so now coming to geometry. Okay, briefly, there are one or two other things in group theory which I want to mention, but let me first show an example from geometry that where all these groups subgroups are going to come. So we have been studying geometric transformation for last few lectures, right? So again, going back to the definition. So what is a geometric transformation? And out of that, particularly, we have been looking at congruence transformation, right? So we have been looking at the congruence transformation. And what we say is a congruence transformation. It is an operation where you take the entire plane and transform it in some way such that congruent objects remain congruent. So for example, we have seen examples of translation. Translation by a vector. So if I choose any vector in the plane, so this is my vector AB, and if I take any point or any triangle and I apply this transformation, like I move the whole triangle from here to here, right? So then the object remains congruent to itself. So this is what we call a congruence transformation. And we also talked about how we can compose transformation, right? If I apply transformation 1, let us say transformation 1 is this translation, and transformation 2 is rotation around this point by 60 degrees. Okay. So suppose I do this first translation and then rotation around this. So with rotation, this triangle will go somewhere over here, maybe something like that. So we have seen these two examples, translation, rotation, and how to compose them. So now with the knowledge of group theory, I can start to ask the question. So question 1 is the set of all congruence transformations group. So if you take the set of all possible congruence transformation, but there is one more element in this which we have not studied, which is reflection. So if you take the set of all congruence transformation, that every possible function which changes the plane in some way, okay, and the operation is composition, that how you can compose to some function, right? Function 1 and function 2, I can apply one after the other. So is this set a group? Okay, so I think we already answered this question as yes a couple of lectures ago, that we saw that if you basically all those laws are satisfied, right? You have associativity because if you have 3 operations, you can do. I mean, first operation followed by the other 2, or the first two followed by the third one. So you get the same answer. So basically the answer of this is yes. Okay, if you don't remember, you can go back and watch that lecture from I think 2 weeks ago that we discussed that this is the answer of this is yes, that it is a group. Okay. But now what we are going to see is that question 2 is a subgroup of, so consider only translation. Okay. And maybe I have not created any symbols for this. What symbols will suggest? Maybe we'll call the set of, so the set of congruence transformation, let me call it as CT. Okay. I don't have any special name for that. So CT is the set of all congruence transformation, and the set of only translation we'll call TR. Okay. So the first thing we'll observe is that TR is a subset of CT, right? Because every translation is a congruence transformation, right? If you translate an object, if you translate a triangle from one position to another, its shape does not change, size and shape does not change. So every transformation is a congruence transformation. Every translation is a congruence transformation. But now the natural question to ask is that, is it a subgroup? Okay. So the property, the requirement for subgroup is that if you take two translations and you combine them, do I get one more translation? If I apply one translation and another translation, is the result as if one big translation? Yes, right? We have seen this. This is the vector parallelogram law of adding vectors, correct? So for example, if you know AB is the first vector and BC is the second vector. So in other words, if there is an object over here, which first I apply translation AB, so I'll get an object like this. And then I apply translation BC, so I'll get an object like this. Can I think of these two combined as one single translation which directly goes from here to here, right? So adding two translations in this way will give me one more translation. So translation is clearly a subgroup of, so using my notation, I don't want to write the whole word. So TR is a subgroup of CT. Okay. First observation that if you take the set of all translations, that is a subgroup of the concept. So the same question we can ask for rotations also. If you take the set of all possible rotations in the plane, that will also form a set. So is that a set also subgroup of the, no, why?
Because two rotations, if the rotation, angle of rotation sums up to 0, then we get a translation outside.
Yes, correct. Right. So we had seen this last time that sum of two rotations is not necessarily a rotation. If the angles are adding up such that it is a multiple of 360 degrees, then you will not get you will get a translation, right? So if I have the same question for rotation, so again I have to create some symbol for the set of all rotations. Let us say ROT. Okay, so ROT is the set of all rotation in the plane. So again, the rotation is a subset of transformation, right? So rotation is a subset of congruence transformation. But just because it is a subset does not mean it is a subgroup. Because I can have two rotations, like we have seen example of this, that if we have, let us say, an object over here, which I rotate through 60 degrees first, okay? Let us say rotate anti-clockwise 60 degrees. So this triangle goes somewhere over here. Okay. And now next step, let me not take the scalene triangle. Suppose the original triangle looks like this. And after rotation to 60 degrees, it looks something like this maybe. So this is the first rotation. And now the second rotation, let us say this is the point O1 around which I did the first rotation. And around O2 now I'm going to rotate 60 degrees in the opposite direction. So now I'm going to be 60 degrees like this. So first was anti-clockwise, next is clockwise. So you see the triangle has become parallel to itself. And no rotation can take the triangle from here to here. So from here to here, a rotation is not there, but a translation is there, right? So therefore, rotation is a subset of this, but ROT is not a subgroup of set. But can we do something to make it a subgroup? What if I took rotation and translation together? Like I can take the union of two sets, right? So consider. So consider.
If you take both, then it will be.
Then it will be subgroup, right? So if I take the union of rotation set plus translation set, and I'll not create a new symbol for this, but will this be a subgroup? Yes, because now any operation, if I take to translation, it is under translation, no problem. If I take to rotation, it is either rotation or translation. What about translation plus rotation? If I translate an object and then I rotate it, will there be some element in this set which will allow me to go from here to here directly? Let us take a concrete example. Translation won't work because now the what you say, the direction of that triangle has changed now. So it has to be a rotation only now. So suppose, so let us take one concrete example. That suppose we take an example of, first let us say I translate by vector AB. Okay. So I start with and I'll take a segment. Okay. So let us say segment PQ is my original segment. So first operation I do a translation by AB. So under translation, so PQ will become a segment like, let me call it P1Q1. So P1Q1 is the translated. Then I take some point in the plane O and I rotate P1Q1 through some angle theta. Okay. So what will it look like? Something like this. The point P will go somewhere over here. And point Q will go somewhere. I'm just drawing the diagram roughly. I don't know. Okay. So first translation followed by rotation. Can I go from PQ to P2, Q2 directly? And clearly you see that the segment has rotated, so translation will not work. But you see there will be some rotation in the plane through angle theta, right? And that point of rotation will not be O, it will be some different point. But we can find out that point, right? We had done this exercise last time also, that if you want to find out what is the center around which the rotation will directly go from PQ to P2, Q2, we can find that point. And the reason we can find it is, we know that under rotation, the distance from that center does not change, right? So here what is going to happen is O is equidistant from P1 and P2. So O lies on the perpendicular bisector of P1, P2. In the same way, whatever is that new center we are asking for, we can take the perpendicular bisector of P and P2, right? If I take the bisector of this, and similarly if I take the bisector of Q and Q2, right? So wherever the two bisectors meet, this will be my new point O2, let's say. Around that point O2, PQ will directly go to P2, Q2. And the angle of rotation will remain theta. So in other words, translation plus rotation can also be another rotation. Okay. Just to show this point in GeoGebra. And when like those who have used GeoGebra will see that GeoGebra is so nicely set up for transformation work. It has all the tools for applying transformation, and that is kind of deliberate because transformations are very central to the theory of geometry. Oh, I looked, opened it 2 times. Okay, so let me take any point A and B over here. It has two different versions of GeoGebra. Okay, so this AB is going to be my first vector of translation. And so, I mean, I need an object to translate, right? So let me take a triangle. Okay, CD is my triangle. I'm going to apply the transformation to this triangle CD. So if you go to down to this section, you see there's a transformation segment here. Transform. You see translate by vector. All these things are given. So like GeoGebra is very nicely built for studying geometric transformations. And let me mark this as a polygon. Okay. So I say translate by vector. So I have to first select that this is the object I want to translate, and this is the vector. So it has moved the triangle by that vector, right? And now let me take any point in the plane around which I move to the rotation. So let us say I take the point over here. So around F, I want to rotate clockwise by 60 degrees. Okay. So again, if you go down here, rotate around point. So I can select object to rotate, center of rotation, and angle. So let us say clockwise, sorry, 45-degree point, sorry. Okay. So the original triangle CDE, first translation to C dash, D dash, C dash, then rotation to C double dash, this D double dash, C double dash. And so the question we are trying to answer is, can we directly go from the original triangle to the final triangle with one single rotation? And so as we said that whatever that point of rotation is, it is going to lie on the perpendicular bisector of D, D double dash and E, E double dash, right? So if I draw the perpendicular bisectors of these two segments, so D, D double dash and E, E double dash. Okay. So wherever they meet, so this point, if I take this as my center and I rotate CDE, it should directly go to this trend, and we can verify that. But in the diagram also it is looking like that, right? Roughly speaking. So if I rotate this triangle around this point, again clockwise 45 degrees. See, I mean, it looking like the same triangle, but it is overlapping with the original triangle. Okay. Okay. So
The G is independent of the.
yeah, we have to prove that G is independent. That is a very good point. And we can verify that in GeoGebra also. So one very interesting thing that will happen here is that suppose I move this triangle CDE, right? The point F will not change because F is our input, but this point G will also not change. So let us try that. See, if I move the triangle, the point G is not changing. So this is the property of transformation. The transformation is independent of the object that you're operating on, because it is transforming the whole plane. You can think of it this way. It is very complicated to draw, but one way to think of transformation is that there is a grid, like coordinate system grid on the plane, right? So the whole grid is getting shifted. So that is why when the whole grid shifts, every point gets transformed, right? So like under translation, I mean, may have heard this concept of shift of origin, right? So under shift of origin, what happens? The whole coordinate system goes from one location to another location. In the same way, this is a rotation of that system. So if I rotate around 60 degrees, maybe under rotation, this whole system gets rotated by 60 degrees. So every single point goes to a different location. Okay. So that is why in the first few lectures, I spent a lot of time emphasizing the difference between the operation of transformation and the object that you're applying it to. Just as the concept of multiplying by 2 is a much more general concept than an example like 5 2s are 10. So the operation of multiplying by 2 itself has some properties. Like, do we all know that multiplying by 2, if I combine multiplying by 2 with multiplying by 6, it is the same as multiplying by 12, right? Any number you can multiply by 2 followed by 6, it is as if you multiply by 12 directly. And it does not depend on specific example. Like if I take 3 and I do all of this, I'll get the correct answer. But even if I change 3 to some other number, this formula still applies. That is the same thing we are doing here, that one translation and one rotation is the same as one more complete rotation, and that which rotation it is does not depend on which triangle you took as an example. Okay, so this point is very important. Okay, so anyway, coming back to what we are, yes.
The example was translation then rotation.
Yes.
And what happens when you do first rotation and then
Yes, that's a very good point, because we don't know whether it's a commutative group or not. So you have to work out that example also, but there also you'll get a rotation. But interesting, it will be a different rotation. You can try this example. If you go back to GeoGebra. So here we know what is the object. So this is the translation vector and that is the rotation. If I start with the same triangle, let us do the rotation first followed by translation. Do you think we'll get the same triangle or different triangle? We can do this. So first I'll rotate around point F with 45 degrees. Okay. So that is exactly the point. This is not a commutative group. So if I rotate this triangle around my center, 45-degree clockwise, I'm going to get this triangle. And in the diagram also you see that this triangle translated through that vector. Look at, see the vector is like this. So after translation, this triangle is going to go somewhere in this region. So clearly it is not the same as our triangle. But that will also be represented by some other rotation. So that center of rotation will be different, but it will be another rotation. So you see the first example of a commutative, non-commutative group. If you go back to the translation, only translation set was commutative, right? If you look at the set of only translation, here we said that translation is a subgroup of city. The set of only translation is commutative. Why? Because addition of vectors is commutative, right? In this diagram, when we said we'll first apply AB, then BC. If somebody says, let me apply vector BC first, right? So you'll come here and then you apply AB. Order does not matter. So translation is a commutative. So I should have written this as a commutative subgroup. But now this new rotation and translation combined is a subgroup, but not a commutative subgroup, right? So I can say this is a, I don't know if there is a word non-commutative, but for now let us just invent this word. Subgroup of our original set of city. So through all of this theory, I hope you are getting the sense that how there is so much algebra happening behind the scenes when we do geometry. There is a lot of algebra that is built in the system, but somehow it remains hidden from us because we don't directly talk with the algebra part. Just as you use a device like a computer, we click on a button, we draw some picture, but behind the scene there is so much happening which we don't know. Computer has circuits, it has so many transistors, but all of that happening behind the scenes, so we don't even realize. In the same way, what I'm revealing is one more layer of geometry, that when we do normal things in geometry, behind the scene, all the transformation, all the algebra is happening. Okay, so we are going one layer deep into the algebra of geometry. Okay, so now one question is, so this rotation and translation together is a subgroup. The question is, are there any other elements left in this whole set city which are not captured in this? Or even at this point, you feel that with rotation and translation, every possible congruence transformation in the plane can be achieved. In other words, if I start with a triangle ABC and I take another triangle A1, B1, C1, which is congruent to ABC, can I always reach that A1, B1, C1 from ABC with some combination of rotation and translation? So if I have to state it as a question, does or is there anything left that we need something else? So if I take an example, the ABC triangle is over here, and I take triangle A1, B1, C1, which is congruent to ABC over here. See, if that new triangle is parallel to the original triangle, then I know that one translation is enough. If it is not parallel, then I know I need to do rotation. But is that all? Yes. What about this triangle? That is fine. You can have any combination of those, but can you reach this triangle always from there?
Yes.
Yes.
By rotation and
Yes.
trans.
Okay. But every triangle congruent to this triangle in the whole plane, you can reach this way? Or is there any triangle which you cannot reach with just these two operations? What about this triangle? Huh. If you see the order of the points ABC, ABC was always going anti-clockwise. Here also it was anti-clockwise, but now ABC is clockwise. But of course, even if you change the order of the points, it can be congruent to the original triangle, right?
So that is not possible.
That is not possible. If you notice, rotation and translation will never change the order of the points. Anti-clockwise will remain anti-clockwise no matter how many times you rotate, how many times you translate. This will never be reached. So we need one more operation called reflection. Reflection in a line. Okay. And reflection is a very interesting concept. You may think that is trivial, right? Like mirror image. If you take an object and a line, you just take the reflection, right? But in terms of group theory, you will see that reflection has some amazing properties. Okay. So we have to create a new, so let, I don't know, REF with a set of all reflections. Okay. So let me define what is a reflection first, because this is the first time we are interacting with this. So as always, we have to have some input object. Like for translation, we have to specify that this is the vector. For rotation, we have to say this is the point and this is the angle. So for reflection, what is we have to say that this is the line. That reflection has to be defined with respect to a given line, right? So we always say reflection in a given line. So if some line L is given and some point is given over here, point P. So what will the image of that point under this operation? If you take the perpendicular and you extend it so that the distance, same distance you take on the other side, right? P dash. So then we say P dash is the image of P under reflection in this line L. So you see every line in the plane will have its own reflection.
Can you write directly P dash is the reflection of point P? The line.
So yeah.
And the word image is not.
Yes, it is not required. And in fact, last time we created like a shortcut notation, like the reflection operation. I think we had written like something like TR for translation, ROT for rotation. So let us use REF for reflection. So if I write REFL, this is the operation of reflecting its line L. So I can write a short form that if I apply this reflection on point P, I get P dash. So this is a like function kind of notation of writing the same. Shortest form. And now, first thing we have to answer is what will the reflection of P dash under the same line? P, right? So reflection is what we call, there's a word for this kind of, no, there's a word for this, is called an involution. Okay. And involution is a function which is its own inverse. That if you apply that function 2 times, you get back the original. I think I may have introduced this word before also. Okay. So reflection of P dash is again P. Okay. And now, we have been talking about this for a long time that instead of writing it this way in 2 lines, I could write it in one single line by saying reflection, reflection under line L composed with reflection under line L. So this composed operation, if you remember, this is just combining 2 translation operation into single operation. So this as a whole, if I apply to the point P, I'm going to get the point P back. Right? You always unpack it from right to left. Okay. So this is reflection in the same line. But what about two different lines? If I have line L1 and line L2, so I first reflect in line L1, then in L2. What will be the result? Depends. Depends on how the two lines are oriented. Okay. So you have to answer the question, what is the result of combining two reflections? Um, yes, okay, let us take two reflections to begin with. Then we are going to see combining n reflections. So here we have to take two cases actually, because depending on the case, the answer will be different. So case one, if you take parallel lines, okay, so the two lines which we are considering, they are parallel. So let us say this is line L1 and line L2. Okay. And so if you start with the point P over here, let us say, so you will first reflect in L1 and then in L2. And so I'll give you some time to think that what is the result. Okay. But what is the geometric transformation? Yes, Anushka?
Yes, sir. If we take a line exactly between L1 and L2 and parallel to it,
Mhm.
then the reflection of P in that line would be the P prime.
No. So you are saying that the combination of two reflections is one reflection.
There is a fine result.
But if you think about how reflection works, right? The fact it is like an odd and even thing. If you start with an anti-clockwise triangle, you reflect once, you'll get a clockwise triangle. If you reflect it again, you're going to get an anti-clockwise triangle again. So how will the single reflection go from anti-clockwise back to anti-clockwise? So Anushka, are you understanding the difficulty? That why two reflections together cannot be a reflection? Because if, let us say, instead of taking only point P, I'm taking a small triangle here, okay? Let us take a small triangle XYZ, okay? So XYZ are anti-clockwise. First reflection, the points are going to become clockwise. And second reflection, they are again going to become anti-clockwise. So starting with the anti-clockwise, you again are getting anti-clockwise. So one single reflection will not achieve this. So it has to be something else.
Okay, got it.
Okay. So this is simple geometry, so I'm not going to give the answer. Take your time, think.
So integral is just one translation.
Yes, but will that distance of translation always be in constant, or if the point changes, the distance also changes? Okay. Try to see if you can compute that distance. How much is that distance?
Be twice the distance between the two.
Yes, correct. So then it will be constant, right? So the distance is going to be 2 times the distance between the two lines.
Now what we have to keep on?
So if you have solved the parallel line case, then you take the non-parallel line case.
This is still one.
नाही ते फक्त ह्याला आलंय बाकीच्यांना नाही आलंय so मी थांबलोय.
Non-parallel line बद्दल त्याला आलंय.
नाही पॅरल लाईनचं त्याला आलंय बाकीच्यांना नाही आलंय म्हणून मी थांबलोय. थांबा 2 मिनिटं थांबा मी प्रूफ देतो.
Parallel is a correct difference.
पण त्याचं प्रूफ काय? Why twice? Why not thrice? Why not 4 times? Huh. So what will the diagram look like? Suppose we start with the point P located here. Okay, so first we do reflection in L1. So let us say we get the point P1. And then I do reflection in L2. So clearly it is going to remain, this P1, P2 are going to remain collinear because these are 90 degrees and we have parallel lines. So they are collinear. But what can you say about the distance from P to P2 directly? If I call this X, X, Y, Y. You see the distance from P to P2 directly is 2x plus 2y. Correct?
That's what it is.
Oh, yes, correct. Oh, which is equal to 2 times x plus y. No? And the important point is x plus y is independent of the choice of P. X plus y represents this distance, right? So therefore, even if you change the point P, the values of x and y may change, but x plus y will not change. So therefore, basically what we are saying is that reflection. So if I denote this vector by some letters AB. So AB is this vector which goes from L1 to L2. Then our composition notation, I can write that reflection in line L1 composed with reflection in line L2 is the same as translation by vector AB. 2 times actually. So reflecting in line L1 followed by line L2 is the same as translating by this vector AB 2 times. And interesting thing, if you see the translation by vector AB, the image of P is not going to go to P1. Where will the image of P go? It will go to some point over here maybe, right? Which is at a distance of x plus y. So first translation will go to here and second translation will go from here to here, again x plus y. But obviously x plus y is the same as x, x, y, y. So therefore finally you end up with the point P. Is this clear? Online?
Yes, sir.
And again, important thing is that if I change the point P, this vector does not change. This is going to be fixed. And I'll show this in GeoGebra. It may seem counted. Some may think that if I take the point P really, really far away, won't its image P2 also go far away? Then how will that vector remain constant? But we'll see what happens in GeoGebra. Okay. But is the proof clear? Okay. So how does this actually work? Let me clear the diagram.
So it's like a subtraction.
It is a kind of a subtraction. Like you will go ahead and you will come back. So effectively it will be cancelled. So let me take the first line here and take a. Okay, so this is my line L1 and L2. So if I start with a point P, okay, and I'll first reflect in the L1. So D reflected goes to D dash and D dash reflected in this goes to D double dash. And so we are interested in let me just draw it as a vector, okay, from D to D double dash directly. Okay, so look at this arrow. So this is the arrow and you see it is roughly looking twice the distance between these two lines. And now what happens if I move this point D? See, even if I move the point D anywhere in the plane, even if I take the point D really far away. So now D, in this position, what happens? D goes to D dash in the first reflection, and from D dash in the second reflection it comes back to D double dash. Effectively, the operation is translating 2 times in this direction. Right?
Yeah.
So generally speaking, always tell that you should not use GeoGebra because it will destroy your ability to draw diagrams on paper. So, but I think transformation is one place where it is really helpful to see all this in action, right? If you visualize the algebra, then that makes it clear to understand. So to that extent, it is okay to use GeoGebra to visualize, but don't make it a substitute for drawing diagrams on paper. So you have to be cautious that when you should use GeoGebra and when you should not use GeoGebra. Maybe someday in the future, it is possible that you will be given access to GeoGebra in the exam. There will be one day that will happen, but not today.
GeoGebra is a free software.
फ्री सॉफ्टवेअर. आपल्याकडे स्केचपॅड होतं बघा CDSI ची, ते आता स्केचपॅड कोणी वापरत नाही, पण GeoGebra मध्ये खूप जास्त फीचर्स आहेत. मी कोऑर्डिनेट जॉमेट्री पण यांनी खूप छान शिकवता येते. कुठेतरी तुम्ही हे एनेबल केलं ना की कोऑर्डिनेट जॉमेट्रीचे ग्रीड सगळे पॉइंट्स प्लॉट करता येतात. मी आपण परवा त्या क्वेश्चनला हेच वापरलं होतं. GeoGebra is very powerful because it also has some programming features that, for example, I can write it because I want to do this construction again and again. Let's say I want to draw the circumcircle every time. Then where will I go to tool and select it? So I can program that as a new tool, that circumcircle tool. So it will automatically do it for me. Okay, so this was about combining two parallel line reflection. But what if the lines are not parallel? So what will that look like? So case 2. So let us say
Be like the
you have to think whether it will be a vector or something else. So let us say the line L1 and L2, and let me draw them a little bit separate. So this is L1, L2. Again, you start with a point P over here. And see what will happen under two reflection, like one reflection under L1 followed by reflection under L2. By the way, one small comment I want to make on the previous part. When we said that, under parallel lines, it is a combined is a translation, and that vector of translation is 2 times the distance between those two lines. And if you go back to the way we started talking about reflection, we said that reflecting around line L goes to P dash, and reflecting around line L comes back to P. But you see, this is a subcase of this, because here it is as if the lines are overlapping, right? So if the lines are overlapping, what is the distance between them? 0. So it is translation by vector 0. So that therefore P comes back to P after that 2 operation. So whenever you do something like this, it's always good to go and check that special case. That is that special case also satisfying the rule. Just for our confirmation.
like a rotation. Angle which is 180 minus theta. Suppose the angle between the two lines is theta.
I call this angle theta.
Then the point P will be P dash.
Mm-hmm.
By 180 minus theta will be arrow.
Why 180 minus theta?
So firstly, you're going 90 degrees to the line here one.
Mm-hmm.
Then you're passing to another line
Mm-hmm.
on the line.
Mm-hmm. Mm-hmm.
You're hitting on the top.
Mm-hmm.
180 minus theta.
Yes, that angle is 180 minus theta. Correct. But is that the point around which you are going to do the rotation, or which is the point around which you will do the rotation? See, if that is the point of rotation, it has to be equidistant from the starting and end point. Otherwise, it will not be rotation.
From the intersection point by angle of 2 theta.
Yes, correct. So in a question like this, always you have to think what is the invariant. In other words, what is the thing that does not change? So the thing that does not change, everybody should realize is that the distance from the center is point of intersection of these two lines, right? Look at the distance OP. Under that reflection, where P will go to a new position, but the distance from O will not change, right? If you draw those triangles, you'll get congruent triangles. So let us say P goes to, let me take the point P a little bit closer. So point P goes to position P1, let's say. And P1 goes to P2. So you see the same thing that we saw here, X, X, Y, Y. In the parallel line case, we are getting vectors X, X, Y, Y. Here we are going to get angles, right? If I call this angle theta1, then this will also be theta1. And similarly, this pair will be both theta2. And again, theta1 plus theta2, this middle angle is our theta, which is the angle between the two lines. And so the total angle from starting, so OP to OP2, so angle POP2 will be 2 theta1 plus 2 theta2, which is 2 times theta, right? And again, I hope you can see the congruent triangles here, that Y triangle OP, if I call this point something T, T1 and T2, then you get congruent triangles. That is why OP1 and OP2, they are all equal in length, right? So OP, so therefore I can say that if I take the point P, and this is one more way of writing transformation. So you see there are 3-4 ways of writing transformation. One is you can write the full sentence that P2 is the image of rotation under so and so. Other is the function notation that we saw, and this is the arrow notation where I write the starting object. I draw an arrow. On that arrow, I will write a detail that what is the operation I'm doing. So here I'm doing rotation हा हा ROT पण लिहू शकतो करेक्ट around O with angle 2 theta. Okay. So you can write ROT also, that is also fine. So around this operation, P will go to P2. Okay. Or if you know, stick to our this function composition, I could also write this as, so now reflection under line L1 followed by reflection under line L2. This combined is the same as rotation around point O with angle 2 theta. By the way, you have seen example of this in real life, maybe. If you have gone to that in a circus, have you seen those mirror hall where so many mirrors are kept at different angles? Or even if you go home and you can try this experiment. If you have two mirrors, you can keep them at any angle you want and stand in front of that. And you'll see your own reflection from 2-3 different sides, right? Reflection of reflection, you have seen that effect. So that reflection of reflection, if you carefully look at the angle, it will be from your angle, it will be 2 times the angle of that intersection. Like for example, if you take like a 60-degree, let us say this is mirror 1 and mirror 2, which is at 60 degree of mirror 1, and if you stand over here, okay, then what will happen is your first reflection will go here. So this is the normal reflection, but in this mirror will also get reflected. So you will have one additional reflection over here. And if you see this one, right, this angle will be 120 degrees because it is 2 times this angle. And so in fact, and this will keep happening. In this mirror will get reflected. So you will get one more copy over here. So total, in fact, you'll get 6 copies, or rather I'll say 5 copies. You are the real copy and 5 other copies. So if you have a 60-degree angle, you are going to get 5 copies of yourself in that formation. Because of this 60-degree, you get a hexagon. If you change this 60-degree to something else, right? Instead of 60-degree, you take any other angle. Accordingly, that whole arrangement will change. Like if you take 90 degrees, you'll get 4 copies. I mean, you one original and 3 copies. So if it's a 90-degree situation, then this will get reflected over here. This will get reflected over here, and this. So you'll get 1 real and 3 virtual objects. So if you make that angle very acute, right? If you take 2 mirrors that are almost parallel, like if you take an image that looks like this, if you take like this, very thin mirror, and you stand in between those 2 mirrors, and now you'll see what will happen. You'll get so many images. And just think of the limiting case. What if I keep doing this? If I keep closing the angle, in the limiting case, it will be 2 parallel mirrors, right? So have you seen this parallel mirror effect? If you have 2 parallel mirrors and you stand between, how many copies do you see of yourself? No, infinite, no? It keeps repeating in both directions. You keep seeing mirror, you'll see your front, you'll see your backside, infinite mirror. So this is like the limiting case of this, like where the angle is approaching 0. Okay, I don't know, you must have seen this effect in some hotels or somewhere where you get parallel mirrors. Okay, so interesting that combining 2 reflections can be a translation or a rotation, depending on whether those 2 lines are parallel or not, right? And again, just to show an example of this in GeoGebra, so let me delete this line. And now let me take any random line, okay, which is no longer parallel. So I'll just take any other point. So first line AB I will not change, but now the second line BC is the second. So first operation, which was the starting point D, right? So first I reflect D to get D dash, and now D dash I want to reflect again to get D double dash. Okay, so this D double dash and D, now if I plot the angle formed by them, okay, it's not looking very clear. Let me just draw the lines. Okay, now look at that angle. The value is given, so 53 degrees, right? So if I rotate, and most likely 53 degrees will be twice of the angle between these two. I just chose any 2 points, so it is not a nice number. but doesn't matter. Like if I change this, let us make it a nice 60 degree. Okay, close to 60. And you see roughly the angle ABC is 30 degrees. So that is why twice of that 60 is coming. And now if I move the point D, see the point D moves, the mirror image moves, and its mirror image moves. But this D and D double dash remain at 60-degree angle, no matter where you put this point. Anywhere, literally anywhere in the plane, doesn't matter. Above, below, it is always going to remain 60 degree. Okay. So therefore, what is the conclusion? That what is the, so we had looked at that third set, right? RES. So RES was the set of all reflections. So the question one, is this a subgroup? Of all the congruence transformations? Huh? No, right? Because if two reflections you take, the result is not a reflection. That is what we are seeing. So clearly the answer is no. Combining two reflection will not give a reflection. But interesting, if you see, combining two reflection is either a rotation or translation. So you see that was the set that we had taken earlier, that rotation and translation combined. This set can be generated by reflection. So in other words, what I'm saying is that suppose you have to go to an exam and you can carry only one geometric tool. Which will be the choice of your tool? It has to be reflection, because you can use reflection to do any rotation you want. You can use reflection to do any translation you want. And of course, you can use reflection to do reflection. You see? So reflections can generate all the other transformations. That is a surprising result. And see, reverse is not true. If I go with only translation, I can never achieve rotation. Even if I go with rotation, I can do translation plus rotation, but not reflection. But if I go with reflection, I can do everything I want. So in other words, what I'm saying is that suppose somebody decided to create a crazy version of GeoGebra where they only gave one tool. Okay, they only gave one tool. They did not give all these three. They gave only reflection. But using reflection, I can create the effect of the other two tools by choosing the suitable angle, suitable lines. Right? And you are going to see examples of this in many domains, that how one object can be used to create all the other objects. So therefore, reflection is not a subgroup, but now if I combine all these three, so reflection, union, rotation, union, translation. So all these three together is a subgroup. Because within this, anything you do, you are going to get the result within that group. Okay. So I want to do some examples of actual problems, but there is one last question which is left unanswered. That is a homework for you. That now are we complete? Now is this going to be the same as the set of all transformation, congruence transformation, or is there something still left? Or combination of all these three will give me the desired result.
I think so.
Okay. Actually, no, sorry, I made a mistake here. This is also not a subgroup. Because we have answered the question reflection with reflection. What about reflection plus translation, reflection plus rotation? Is that also within this set or it is outside the set? So actually, this is not true. This is not a subgroup. So again, this is a homework for you, but consider this example. Consider reflection plus translation. And to keep things simple, I want to use that translation vector along that line. Okay. So like if I take this as my line of reflection, I'll choose my translation vector parallel to this. Okay. Let us say AB is my vector. So what is the operation I'm suggesting? Start with the point P. First reflect the point. Okay, and okay, let me not take point P. Let me take a triangle PQR. Okay, so let us say triangle PQR is taken. So first I reflect in this line. So I'll get a new triangle roughly here P1 Q1 R1. And now I'm going to translate this triangle with vector AB. So I'll get a triangle like this, right? Roughly speaking. So now the question you have to answer is, can I go from PQR to this triangle directly with a single operation? So it may appear that clearly the order of points is reversed. So I have to use reflection. With only rotation and translation, I can never achieve this. But can I even achieve this with reflection or not? So the answer is not always actually. Sometimes it is not possible to go from here to here directly with one reflection. So reflection plus translation is not under reflection. So then what is it? Okay, so this is a homework for you, that figure out that what is the answer of this question. What is the result of reflection plus translation? Okay. But in these 3-4 lectures, basically we have almost covered the theory part of Yaglom 1. So the transformation book 1, these are all the 3 basic operations that you need to know: translation, rotation, reflection. Okay. And now we are going to see how is this useful to solve problems. So typically for construction problem, this is very useful. Okay. Some particular construction problems can be done very nicely using transformation. And they can, we already see one example last time that you took a triangle, on the 3 sides you draw equilateral triangle or some other triangle. But now let us consider one more example. Okay. So this is what is given. Given a point P and lines L1 and L2. Okay. So any lines are given. They will not be nice lines. So any lines L1 and L2 are given, and some point P is given in the plane. Okay. So what you have to do, using ruler and compass, construct triangle PQR, which is equilateral, such that point P is already given, but first point has to lie on line L1, second point has to lie on line L2.
take any point on this line and draw perpendicular concept like a draw line perpendicular.
No, but yeah, we don't know. See, what is P need not be on the angle bisector of L1, L2, right? P can be anywhere. So I won't give the solution yet, but just to talk about
What was it in that discrete pointer?
okay. Okay.
Center
Okay.
I is equal to OK.
Okay.
And the R.
Okay. See, the difficulty here is I want first point Q on line L1. If I choose any point I want, I can draw the equilateral triangle. The problem is the third point will not be on L2, right? So I have to choose that point Q in a special way so that the third point will automatically lie on L2. And I cannot keep doing trial and error with infinitely many points are there. So how to find that special point Q so that automatically the point will go on L2. And remember, we are doing geometric transformation, so think in that direction. So in this, sometimes it is useful to draw what is called auxiliary figure, right? Suppose you have completed the construction and roughly by hand, let us do it. It may be something like this. Okay, so let us say the point Q is over here, point R is over here. So looking at the completed diagram, does it suggest some properties that it is an equilateral triangle? Most importantly, it is not any triangle. So it is an equilateral triangle with all sides equal. So first thing we would like to do is start to describe the diagram in terms of geometric transformation. Like triangle PQR is equilateral. How many different ways can you say equilateral? One can say that all sides are equal, right? Somebody can say that all angles are equal. Equal and 60 degrees. Like that. So many definitions of or description of equilateral triangle can give. But can you give a description in terms of geometric transformation? Yes.
As you move the Q,
Mm-hmm.
that translation of it,
Yes.
the line is
Yes.
that much distance R goes to R
Yes.
on the line is.
Correct.
And if the point B, it's rotated by some angle.
Uh-huh.
Again, we can maintain that equilibrium.
Yes. Correct. Point, I will say point P will not get because point P is fixed, right? So keep point P fixed and look at what is the connection of Q and R. Point P तो दिला है ना, given point P. This point is fixed. You are saying something, Rohan?
Yes, sir. In terms of transformation, you can say that a rotation around P of 60 degrees.
Yes.
That transforms to R.
Correct. So can I say that, and like if I just want to write it in the arrow notation, if I start with point Q and I do rotation around point P with angle 60 degree anti-clockwise, right? So I'll just say plus 60. Our convention is positive is anti-clockwise, okay? So this will take Q into R, this rotation. If I rotate around point P with 60 degree, Q will go to R. That is, and you see this is a equivalent definition of equilateral triangle. If you take any point P, doesn't matter this diagram, any point P, any point Q, and to this point Q you apply this 60 degree rotation, the point R you are going to get, this is going to be equilateral triangle, right? So this is one more description of equilateral without using sides are equal, angles are equal. This is another way of saying that a triangle is equilateral. But how does that help us in our question? Because we don't know where the point Q is. But what I want to point out is, although we don't know point Q, do we know the locus of point Q? Locus meaning what is the set on which point Q is going to lie? That is line L1. So the idea is you can apply transformation to one point, but you can apply transformation to whole set also, right? So instead of rotating the point Q, because I don't know where point Q is, can I rotate the whole line L1? What will happen if I rotate the whole line L1? Yes, correct. See, to rotate line L1, I don't need to know where point Q is. And under that rotation, what will happen? The whole line will change. In that process, Q will also go to point R, right? So that rotated image will look something like this maybe. And I'm going to rotate 60 degrees, right? So roughly speaking, it will look something like this maybe. So this is L1 dash. So L1 dash is what? I start with line L1. I apply that same operation, rotation 60 degree around point P. I'm going to get line L1 dash. And what is the usefulness of this? I know that the intersection of L1 dash and L2 has to be point R. So you see how transformation gives a very powerful way of looking at the geometry now. I did not know where point Q is, but what I know is Q belongs to L1. And so R has to belong to L1 dash. I have a very nice phrase for this. I always, whenever I have to give, like in training camp, sometimes I have to give a handout, like a worksheet. I always write this phrase on the text. So this is what I say, the locus of the transform is the same as X. The locus of the transform is the same as the transform of the locus. I will explain what this statement means, but this is an example of that. Basically, what I'm saying here is that I can draw this like a diagram that originally point Q was here and Q belongs to L1. So in other words, the locus of Q is L1, right? And R is on line L2. Oh, no, not L2, L1 dash. Okay. So I can go in two directions. I can first apply the transformation to Q to get the point R, and that will lie on this locus. Instead of that, I can take a different path. I know Q lies in this locus. So I'll first take the locus of Q, and to that I apply the same transformation. I'll reach the same position. So I can go this way or this way. I'm going to reach the same result. So that is what I say, the locus of the transform. So in other words, in this direction, I'm going to do the locus. So this is the locus, right? This is locus, this is locus. And this is the transform. So you can go from here to here or here to here. You are going to reach the same position. And so we don't have time today, but next time we are going to apply this concept again and again to solve many different kinds of problems. Okay. Again, just to revise. So what is the final solution? What are we going to actually do to solve this question? We have the line L1 given, L2 some other line, some point P is given. So I'll first rotate the line L1 60 degrees. So how will I do that? With ruler and compass, how do I rotate a line? You can take 2 points on that line, rotate those 2 points and then plot a line. Or more easily, what I'll probably do, I'll just drop a perpendicular. and I'll just rotate this perpendicular point. So if I call this point T, I'll just rotate the point T. In other words, I'll complete this equilateral triangle. So T will go to T dash, and under rotation, what will happen? The line L1, the PT will go to PT dash, so the line will remain perpendicular, right? So here, if I draw a perpendicular line like this, and unfortunately, it's looking close, but anyway. So this is my line L1 dash, and wherever L1 dash and L2 intersect, so this is going to be my point R. And once I know point R, from there I can complete the PQR triangle. Okay. Right? Let us do this in GeoGebra once so that everybody is clear. So what is given? I'm going to take any line L1 and any line L2, okay, and any point P. Okay, so the names are different, but let it be. So through this point E, I have to draw equilateral triangle. So I have to rotate this line around point E to 60 degrees, right? And let me take this, like something like this, so that after rotation it remains within the goal. So now instead of doing the construction, I'll use this tool. But anyway, you can do it anyhow. So if I rotate this line around E anti-clockwise 60 degrees. Okay. So this line rotated, and so this is my L1 dash. So wherever my L1 dash intersects the second line L2, so I am claiming this is my point R. Okay. And so if I take EF as two vertices, then the equilateral triangle, the third vertex should lie on the line AB. So let us do it simply by constructing the circles. You see those two circles are nicely intersecting on my line AB. So that is my equilateral triangle GEF. आपलं F सेंटर घेऊन FE रेडियसचा आणि E सेंटरचा EFचा टू गेट द इक्विलॅटरल ट्रायंगल. हां, हे टूल आहे ना, हे तुम्ही म्हणजे यू कॅन सिलेक्ट अ पॉइंट अँड another point on the surface. So you see you're getting, and now if you move the diagram, still the construction will remain valid, right? If I change anything in the diagram, it is nicely, you see all the 3 points are nicely lying on the 3 locus. Okay. And something very important about this proof, see that 60 degree could be replaced by any other angle. So can you go home and try this problem now? Same thing, everything is the same, but only I'll change one word. So again, given line L1, given point P, lines L1, L2. Okay, so the setup is the same, point and two lines. But now you have to construct a 45, 45, 90 triangle. Okay. So you have to construct a triangle like this. PQR. Again, Q lies on one vertex, one line, R lies on the other line. You see, this problem can be done also in a very similar way. Only thing that has changed is that now to go from Q to R, the angle of rotation is not 60 degree, but 90 degrees. So now you have to rotate the first line by 90 degrees, and where it intersects, you will get point R. So you can replace that, basically any isosceles triangle you can draw now, right? If I know this angle theta, then I know that under rotation, Q will go to R under rotation around point P with angle theta. So for any angle theta, I can solve this problem now. Okay, so one last question. We won't have time to complete this question, but let me just give you the problem and you can try to think on your own. We will discuss next time. But most important, start to appreciate the algebraic structure behind the geometry, that all these groups, fields, everything, it is coming. काय काय 11 सेंटेन्स हो हो Okay, so I'm going to suggest you to try this problem. This is IMO shortlist problem for 2013. Okay, so IMO shortlist 2013 question G1. So G1 is the simplest question of that shortlist. It is so triangle ABC, acute its orthocenter is given as H. Then W is any point on side BC. Now, when they say side BC, I don't know whether they mean segment BC or line BC, but we have to figure it out. And so let X be point on circumcircle. You know this symbol, right? Circle with a dot is circumcircle. EWN. What is M? I think M and N are feet of altitudes. So these are the feet of the altitudes. I'll draw the diagram later to be clear. Diametrically, obviously. And similarly, let X be the point on circumcircle EWM. Diametrically also. So that I just draw a small diagram on the side. So W is any point on this line. And if you consider the circumcircle, so X is the diametrically opposite point on this side. And similarly, Y is the diametrically opposite point on this side. And the diagram also roughly you can see that if H is the orthocenter, then X, H, Y are between collinear. Okay. So actually this problem can be solved without transformation also, but the transformation proof is very nice. It gives some nice ideas. Okay, but I guess we don't have time to discuss this today. We will discuss it next time. Okay, so just one thing I wanted to know. So in transformation, one topic called homotheity, which I have not covered, but have you already studied it from somewhere? Homotheity to some, it was done. Okay, online, can you raise your hand? Anushka, तो केला का homotheity? नहीं. Okay, ठीक है. Online only one or two. So okay, I will briefly cover it because everybody may not know that. So next time I'll cover that, but after that we'll focus on solving more and more problems. Okay, that's all then. Thank you. Bye.
Sir, thank you, sir.